it's also an information networks. So in that sense, I think it fits to the Center of Network Intelligence seminars. So here what we'll talk about is this quantum computers have some inherent limitations due coming from something called noise and decoherence, and that poses some constraints. So converse, as you all know, in information theory, it means something like limitations, the fundamental limits of understanding how well it can compute. Okay, so I'll explain all the terms as we go forward, and as my abstract mentioned, I don't assume any prior knowledge of quantum of any kind. So in that sense, I should apologize to the experts who already work in the area. But I think still, despite that, they will get something interesting out of it. Though I won't put it in a very, very technical terms. I'll keep it a little bit simple and intuitive. Okay. So this talk, as I planned, is a Converse for fault-tolerant quantum computation. This is a joint work with Uttara Kalyani, who is a PhD student at IIT Madras, and Anuj, who is a PhD student at UIUC. But last night, I realized that the same talk, similar talk, a very, very similar talk with the same title, I gave at Links Paris, and that's also on YouTube. So I wanted to make a little change because this will also be on YouTube. So what I'll talk about, I'll add a little bit of a very recent result that I have done. So just kind of a touch of it to make it a little different. But it also gives an interesting story, which will be interesting. So we'll talk about two converses. And in the second part, Love Varshni from UIC is also is a joint work with him as well. So let me start. So the summary. So I first wanted to give a one-page summary of the whole talk, which is the first thing that we all know, that it's kind of a folklore now, that quantum computers can solve certain problems faster than classical. This faster is in quotes because it's not a complexity theoretic sense faster. It's like for certain classical problems, classical algorithms are not known to work very well, but quantum algorithms are known to work very well. Just like say for factoring is the most promising example which people discuss all the time for quantum computers. But said that, so in practice, when it comes to practice, there are certain issues. The biggest issue is quantum computers build on something called qubits. In classical computer, there is bits. In quantum computer, there is qubits, and they go through something called decoherence. So their kind of quality deteriorates very fast with time, and which you can also term as noise. And this can really derail the computation if the noise is not handled carefully. So that poses a challenge. The way to handle this noise is so something called quantum fault tolerance. Like there are faults, there are noise, but can I make the computation tolerant to the fault? And the way it's achieved is that they put something called redundancy. We all know in communication, the way to achieve kind of counter noise is to put redundancy. So all error correcting codes theory is there to handle that. And so reliable computation, what has been shown in fault tolerance, that reliable computation in quantum computers are possible if the noise, I'll describe what the noise is in a technical term. What it means in this case intuitively, that if the noise is not too much below a threshold, then fault tolerance is achievable. And it's generally done using something called, for every computation, you can, when you're computing for qubits, you can think of computation is done on something called logical qubits, which are kind of realized using multiple noisy physical qubits, which are like real quantum objects, these physical qubits. And logical qubits are realized by joining them together in some coding format. Okay, nice coding format. Okay. So and people are generally interested in understanding how many physical qubits do I need if I want to do a logical computation of say n qubit. So do I need n square, n cube, or some constant times n? So people are wanted to understand that, and that results are called converse. Like what is the minimum ratio between physical and logical qubit that I need to make sure my quantum computation is fault tolerant. This is called the converse results. So as you know, in capacity results in communication, this is the ratio of number of channel. This is the ratio of number of information bits that you're able to send divided by channel use. So you can think of physical. Uh, so that's the capacity. So redundancy is 1 by capacity. Okay, so you can think of number of channel uses divided by the amount of Shannon information that you're able to send. That's you will call the redundancy for that channel. The same way for quantum fault tolerance, the number of physical qubits is like the number of channel use, because that's the real resource that you're using, divided by logical qubits, which is the kind of the information that is going through the circuit. Okay, so you want to understand what's the lower bound on that. And you also want to understand something like upper bound on noise threshold. Remember previously I said that this noise threshold is something like beyond which computation is not possible. So you want to understand the upper bound on it, beyond which no reliable quantum computation is possible. Okay. This talk is, as the title suggests, is about the converse. And what we did particularly in this talk, what I'm going to talk about is better converse bounds on redundancy and noise threshold using finite block length quantum information theory. So we try to connect this, as I have been talking about, as already being setting up the connection between communication and circuits. We try to exploit that connection better in a more formal sense to get a converse bound on redundancy, the minimum kind of a lower bound on redundancy and upper bound on noise threshold using finite block length quantum information theory. So what do I mean by better? Here, what do I mean by better is mostly the known bounds are asymptotic in results nature, like the number of logical qubits are going to infinity. So we make a non-asymptotic bound so that it's applicable to the modern NISQ era devices also, which are of the size of around hundreds or less. It's a tighter bound, like tighter than the existing ones, and it also works for non-i.i.d noise, and it works for general noise too, like not necessarily only one kind of noise. Most bounds are for depolarizing noise, but our thing works for general noise. And there is something else also which I'll touch upon briefly, is there is these two things, like in a quantum computer your desired output can be either quantum or classical, and depending on that the bound has to change. And what do I mean by that? Let me little bit detail on it, give a little bit of a detail on it. So a slide detailed on this classical versus quantum output. So all of we know about this quantum computation solving factorization problem, which is the hot problem. There are many other problems like phase estimation, discrete log. And these are also the problems where the final output is classical. Like think of the factorization problem. Your input is classical, it's a number, and you want to factor into prime factors. The outputs are also classical, they are also numbers. Okay. So here the intended output, final output is classical. But all these algorithms, this phase estimation, factorization, discrete log, they have an important quantum engine inside them. So all of them use a very important quantum engine called the quantum Fourier transform. Okay. So quantum Fourier transform, you can think of all these algorithms are using this quantum Fourier transform as an internal block, and all of these algorithms call to this quantum Fourier transform. Quantum Fourier transform is something interesting, but the state or the input to this engine and the computation engine is quantum, and the output is also quantum. Okay, so it's like qubits are input, qubits are output. Okay. And suppose you want to make some kind of a little bit versatile quantum computer. So in that case, what will happen? You have to make a quantum Fourier transform, and all these algorithms, phase estimation, factorization, discrete log, can be implemented on that computer by doing some pre-processing and post-processing. Because quantum Fourier transform is in the heart of all these problems, but you can do some pre-processing and post-processing to get all these algorithms like phase estimation, factorization, and discrete log. So in some sense, there are certain versatile quantum computation engines where the intended output is quantum, because this is being used by many different problems. Okay. And most of converse results actually, that's why focus on this problem, because this is some kind of a versatile engine and everything focuses on that. If you can make sure this thing is working well, then most likely the rest of it will also work well. Okay. So that's why people focus on this one. And we'll also focus on this one. But I want to differentiate between when you want to doing a general purpose quantum engine versus you are kind of solving for a particular problem, like a phase estimation problem in particular. Things can be quite different, especially when it comes to the redundancy and the converse bounds and the way you achieve them also. Because simply when you're doing a quantum engine, the input is quantum, output is quantum. There, the criteria for fault tolerance, that kind of getting a good accuracy, is something called state distance. Like the quantum state that you're getting and the quantum state that you're supposed to get, a distance between them. Okay, a distance between them in some kind of an Hilbert space sense. That's a criteria. But when your desired output is classical, like the factorization problem, your criteria is probability of error, because you are looking for a number and you are checking whether it matches or does not match. Okay. So the bounds on redundancy are also different. Okay. So this is something which is, as I mentioned, this is the work that we did little later, and I'll just touch upon it a little bit. But for most of our talk, I'll be focusing on this part. And almost all the converse bounds, like all the converse bounds that I know of or we know of, are actually on this part where the input is quantum and output is quantum. Okay, I'll touch on this part a little later. Okay, so but let's focus on this one. Now, what is the computational model? Okay, so the computational model, as you all know, in classical, the computational model is we have a string of bits, classical bits as an input, and you do some computation, and the string of bits is an output. Quantum is not very different from that in this block diagram sense. The only thing is that instead of string of bits, you have something called string of qubits. And qubits are not like 0, 1, they are a little different. So each qubit, so this is a very simplified way of looking things, but I think this helps, especially for engineers like us. It helps to look at this way. There is a Hilbert space way of saying things, but I think this simple way will make a lot of sense. So one way of thinking of a qubit is just a matrix, a complex matrix of two dimension, like 2 cross 2. This has to satisfy certain properties. It's Hermitian. It's positive, means positives definite, and its trace should be 1. And in addition, if you want to get something called a pure qubit, its rank should also be 1. But you can ignore this part, not so important. But this is the one way of looking at qubit is this condition. 1 qubit. Now, if you look at n qubit, the things become something interesting. A system of n qubits is no longer now is defined by a matrix whose dimension is 2 power n. Okay, so it's exponentially scaling. So that's the interesting part to know. So 1 qubit dimension is 2, n qubit together, it's described by a matrix, a complex matrix again, whose dimension is 2 power n, but it should still satisfy these properties: Hermitian, positive, and trace 1. And again, if it's pure, it should have rank 1. So one special case, in special but interesting case of n qubit system is n independent qubits who are not in some way coupled, and they are given by something called tensor products. Okay, tensor products of this n two-dimensional matrix. And as you know, if you do tensor products, you will get a dimension of 2 power n. So this is as an input given to the system. And the operations that we are generally interested in quantum computer is something called unitary operations. So what is that? Now this U is a unitary matrix of the same dimension 2 power n, and U dagger is its your adjoint. So you put rho n inside here, U dagger, and that's what you expect as the output. So almost all quantum to quantum, like say for example, this quantum Fourier transform is also doing something like this, where the U is, for every operation, the U might be different. Okay. So this is a quantum computational model in comparison with classical computation model from the block diagram point of view. Now, as you all know, in classical, this block F is realized using Boolean gates. Okay. So the way these gates operate, they have G inputs, and each of them has one output. Okay. And they can only do Boolean operations. And output of a gate can be copied to multiple inputs to multiple gates and so on. Okay, so this is the way our Boolean circuits work. That's where the quantum circuits differ quite a bit. Here, it also has quantum gates, but these gates has G inputs and G outputs. Unlike classical, which has one output, here the number of outputs are also same as number of inputs. And these gates can only do unitary operations. Okay, so it's just like a unitary U row U dagger, some kind of, but now of dimension 2 power G, because it has G inputs. So the dimension of this U will be 2 power G. And but there are certain restrictions. For example, you cannot copy a qubit in general because of something called no cloning theorem. So copying is not possible. Not only that, you cannot really observe a qubit directly. So there are some ways of doing indirect observations, but you cannot really directly observe the qubit without disturbing the qubit. Okay, and that makes things tricky when there are errors. In classical, when there are errors, you can see and check whether there is an error. In quantum, you have to do it indirectly. Okay, there are indirect ways of doing it, but you cannot do it directly. So these are the, I would say, the analogy between the two models, and the models differ in some cases. Okay, are things clear so far? Is there any question? Is there any question so far? Hello? Hello? Am I online or?
Yes,
There are
yes.
no questions so far, Avhishek. Please continue.
Oh, okay, okay. Thank you. Thank you. Thank you very much. Okay, okay. Yeah, sorry. Okay. So now, one thing I just want to mention, as I said, that see, as you all know, the main motivation for quantum computers, everybody says, is factoring, right? You want to factorize. It's a huge problem you want to solve. Now, how do you use this quantum computational model for solving that problem? So we have discussed this model, quantum computation model, where this is n qubit, a quantum state is an input, and n qubit is an output. The way you solve the classical problem, you have the classical input, which is, suppose in factorization, it's a number, you can represent it in binary bits. You map that classical input into some useful quantum state. Okay, so you do it cleverly, and then you run a clever algorithm like this quantum Fourier transform and something more, and you get a quantum output. This algorithm is designed in such a way that you get a particular kind of quantum output, and from that quantum output, you can get the classical state back through something called a measurement. Okay, a quantum measurement, which gives you back the classical state. So both this mapping to the quantum state and this mapping from quantum to classical has to be done intelligently, including this inside algorithm. If you do it well, as in the case of factorization or Shor's factorization algorithm, you can solve certain classical problems faster than all the known algorithms in the classical domain that exist for that problem. But this is not the focus. As I said, our focus is just on this part, quantum input and quantum output. I'll touch upon this particular problem later, where you have desired output is classical. But our focus is quantum input and quantum output. The reason for that, as I said, this is a versatile engine like a quantum Fourier transform. It's being used in many problems, factorization, phase estimation, discrete log, many things. Not only that, there is another very important use of this problem, especially for physicists and chemists, is that you want to numerically emulate certain physical and chemical processes, certain quantum mechanical, physical and chemical processes. You need a quantum computer whose input is quantum, output is quantum. So for both these cases, this scenario is important, and that's why you'll focus on this scenario first. Okay. Now, before I go there, as I said, our main goal is fault tolerance, but I have not talked about how does noise impact the computation. I give you the computation model. Now we have to study how the noise impacts the quantum computation. So what is noise? As I said, in quantum, there is this qubits, and qubits are prepared using some physical state. It can be some spin of an electron, or it can be state of a photon. But because of interactions with the environment, the state kind of deteriorate, or it's called decoherence. And not only that, these quantum gates are also not so reliable. So gates also fail. So without getting into too much of the physics of it, which I also do not fully understand, I'm not a physicist. So the way generally it's modeled by physicists and engineers and computer scientists is you can think of the failure or the noise of, so you are now doing a noisy gate operation on a noisy qubit and the gate may also fail. The way they model it is a very simple model. It's like think of that you are doing a perfect operation followed by the perfect output of the gate. So the gate is perfect. The output which is coming out of the gate is then going through something called a noisy quantum channel. And that emulates the noisy gate operation or the gate failures. Okay. And that's kind of an universal model that everybody uses in for noise in gate-based computations. Okay. So it's again to think of there is a perfect gate. So noisy gate is modeled using a perfect gate followed by a noisy channel. So the perfect output is going through a noisy channel and you are seeing the perfect output after the channel. Okay. So this is actually quite motivated by a classical body of work exists in noisy circuits, which started by none other than von Neumann, who was very much inspired by Shannon. So it's kind of a similar model. If you're familiar with that model, this is a very similar model. But what is a noisy quantum channel? You all know about classical channel. The way noisy quantum channel is modeled, I'll start with an example because this is the most well-known example called depolarizing, and it's easy to explain in terms of examples. So think of a k qubit system. So rho k is a k qubit system which is a matrix like in a dimension 2 power k. So if this rho k goes through a depolarizing channel, depolarizing quantum channel, then its output will be something like 1 minus p rho power k, where p is a number between 0 and 1, times p times identity matrix divided by 1 by 2 power k. So, so this is a special form. In general, it will be a function of rho of k, some function of rho of k. Okay, but I think depolarizing is a very good example to kind of get it intuitively understand it. Okay, one way of looking at it is you can think of this as a convex combination of rho power k and this identity matrix divided by 1 by 2 power k. So identity matrix divided by 1 by 2 power k is actually also a quantum state. It will satisfy all the properties, Hermitian, positive, and trace being 1. So you can think of what you're getting as an output is a true state, convex combination of the true state that you desire, and another state, which is this identity. Why they choose this state? Now, this state is something called in von Neumann entropy sense is the maximally entropic. Okay. So you can think of depolarizing noise is doing something like it's changing it's making it a convex combination of the right state and the maximally entropic state. Okay. So one particular example of this k bit. So now this is an example of a channel which is working on k qubit. So it's a kind of a k qubit channel. So for if you put 1, you will get a 1 qubit channel. Okay. So one particular example of interest of a k qubit channel is something called i.i.d noise channel, where the k qubit noise is something called a product form of 1 qubit noises. Now this product form is not like the probability product form that we see in classical, but it actually can be interpreted in that way sometimes, and that helps. For example, if you look at also this also the depolarizing noise, there is no probabilistic operation here. This is a totally deterministic operation. There is no probability here. It's a convex combination. But the problem in quantum is this is though deterministic, it's irreversible. The reason is in quantum computers, you are only allowed to do unitary operations. And there is no way through unitary operation you can get back from this output to the original input. So that's why it's deterministic but irreversible and kind of a non-unitary, so you cannot go back. So that's why it's a challenging. It's not that it's probabilistic or random, but it's deterministic and irreversible. That's why it's challenging to deal in quantum, because you can only do unitary operations and noise is non-unitary. But said that, it always makes a lot of sense or intuitively to see this noise as some kind of a probability mixtures between the true state and the most entropic state. So many algorithms, many fault-tolerant schemes are devised based on this intuition. So you can imagine it as some kind of a mixture of the true state and the most entropic state. Now, how do you use this thing in modeling noisy computation? Sorry. So as I said, a quantum computer is this series of gate operations where each gate has G input and G output, and they are all unitary. So rho n is the input. First you do some operations, then another operations, then another operation, and finally you get an output. Now, in presence of noise, each of gate behaves like a true gate followed by noise. So they behave in the following way. So they will be a true gate followed by a noisy channel. And n power g means this n power, this is a tensor product. This means this is a g qubit noise, but it's i.i.d noise, i.i.d across these qubits. Oh, sorry, I am just sorry about it. I'm just making some. Okay. So in each layer, after each gate, you will have that, and hence the final output will be pretty much disturbed. It won't be the true thing that you expect. And the way to get the true thing is by adding redundancy. As we do in error correcting codes, you have to add a redundant qubits in a clever way. Not only that, you may have to add redundant gates in a clever way, and so that you get an output which is close to rho n. So in this setting, the goal is the following. You have to the goal to design a quantum circuit in such a way that, remember, this u rho n u dagger is our original intended output, and qc rho n, as we saw in the previous slide, is the output that you are getting because of the noise. And after adding our redundancy and everything, we want to make sure the distance between these two is less than some epsilon, which is a small one for all inputs, all pure inputs. You can, okay. So where rho n is rank 1. Okay. So that's the goal. Now the way to achieve, as I said, was to add redundant qubits and gates and modify the circuit architecture also. You are free to do that. And there are schemes, well-known fault-tolerant schemes, which achieves certain good redundancy. Like, for example, the total number of physical qubits that you need by n. N is the number of logical qubits, because is actually polylogarithmic in n. So you are having a redundancy which is polylogarithmic in n, which is not very bad. This was kind of a classical results. It was started by Shor himself, then Kiatev and Itaev, then Gottesman, Preskill. Many people have contributed. It's a large body of work. Recently, it was shown that in 2014 by Gottesman, followed by Fauzi, that actually you can make this polylog n as a constant. Okay, so you can achieve constant redundancy if the noise is below a threshold. So if the noise is low enough, you can do all those things. But our goal in this paper, in this talk, as I said, is to understand lower bound on redundancy and noise beyond which fault-tolerant computation is not possible. So we don't want to give a scheme which will achieve something. We want to show a fundamental bound below which redundancy cannot go. Okay. And also find a noise threshold beyond which quantum computation is not possible. So far, people have shown a noise threshold below which quantum computation can be done. We want to show something like a noise threshold beyond which quantum computation is not possible. So it's all converse results, so in some sense negative results, but we are all used to this kind of negative results in communication. Okay, so this is in that flavor. So what is done so far in terms of these converse results? So the first converse was started by Harrow and Nielsen, who showed the results were derived for depolarizing noise. Okay, so remember this P. They showed if P is more than 0.74, you cannot achieve quantum. You cannot do accurate quantum computation. Fault tolerance is not possible. Then the bounds kept improving. So here all these bounds are improvements, where G is the number of inputs to a gate. Okay. So the most recent bound before us was by Fauzi et al. They were the first to actually connect this problem to a communication problem. Okay. And they showed actually the bound should be in terms of quantum capacity of the depolarizing noise or any noise in that case. And quantum capacity, we all know, just like classical capacity, number of qubits reliable is transmitted by number of channel use. Okay. So in channel capacity, it's a classical bits reliably transmitted by the number of channel use. Here it's quantum bits. Okay. So they were able to connect that, and they show whenever quantum capacity becomes zero, reliable computation is not possible. And they did extend it to any general noise. Okay. Not only that, so far all these results were actually on upper bound on noise threshold. Fauzi et al. Also gave a bound on the lower bound on redundancy. They said that if the quantum capacity is qn, then you need at least 1 by qn redundancy. Okay. So in that sense, this result is interesting that we saw this result, or this result came up when we are actually in the midway of our work and we had most of our results derived. And when we first saw this result, we thought, okay, what we are thinking that to connect this to a communication problem, they have already done it. So we are done. We felt bad that they have done it, but we also felt good because the thing that we are thinking also was thought by Fauzi and Muller, Hermes, some of the big names in the area. But then while reading the paper, we realized that our approach, being totally independent from them, had certain big main differences. Many differences. The main ones are, uh, so we do not assume something called a perfect precoder and perfect decoder at the end of the circuit. Our bound actually is gate size dependent. So their bound only depends on quantum capacity. Our bound also captures gate size dependent and some quantity which is closely related to capacity. Their bound is asymptotic, so it's applicable when the number of logical qubits is going to infinity, and the epsilon is kind of going to zero in some sense. Um, but our bound is non-asymptotic, and also our bound extends to non-i.i.d noise, certain kind of non-i.i.d noise directly without any effort. So then we continued to finish it, and we got this, and what we got we'll talk about. That's the next slide. So what we got, a lower bound on redundancy. For epsilon, remember this epsilon is the accuracy criteria. For epsilon below 0.11, we could show that the bound is this. So this bound, first part, is true for any n. N was the number of logical qubits on which you are doing the operation. It's true for any n. But as n goes to infinity, if G is the gate size, it's sublinear in n, then this converges to G by this. So this is a nice clean form, so I wrote down, but this is the general bound. Okay. And what is this IC? So this is the main term, as it clear. This is something called the coherent information of the channel. So the way it is given, so this S is called von Neumann entropy. So for now, to understand, I won't define von Neumann entropy. It's a generalization of Shannon entropy to the quantum state, quantum scenario. But one way of understanding this expression is instead of S, you put H. Okay, and think of all these things, rho G, Ng, rho G, as random variables like X and Y. Okay, so think of Ng, rho G is our Y in classical communication, and rho G like X and this like Y. So this is like Hy minus Hx given Hx comma Y. Okay. So this is actually nothing but negative of conditional entropy. Okay. So then I'm maximizing it over all inputs. So you may say, oh, it's negative. That's the tricky part in quantum. Unlike classical, where conditional entropy is always positive and hence negative of conditional entropy is always negative, in quantum, conditional entropy can be negative. And when you maximize, it definitely will be a positive quantity. So I0 in G will be a positive quantity. And that's a little freaky thing about quantum. And this is because of something called entanglement. In classical, you only see correlation. In quantum, you see something more than correlation, which is entanglement. Okay. And because of that, this weird looking quantity, which is supposed to be negative intuitively, is actually positive. Okay. Now, how does this bound, this G by ICNG, compare with previous bounds, especially the Fauzi's bound, which is the best known bound so far? Is that what is known is the quantum capacity. Remember, their redundancy bound was 1 by quantum capacity. is actually can be related to this ICNG using this expression, this infimum over all k. And clearly, as this is an infimum, this quantity will be greater than equal to, and in most cases, it's a strict inequality. So that way, our bound is non-asymptotic, but when it goes to the asymptotic limit, it's better than the existing bound. Okay. Okay. So, and also we get our noise threshold also. So they got the noise threshold by getting quantum capacity. Whenever it's zero, you get a noise threshold. But no, thanks to this expression, whenever quantum capacity is zero, ICNG is also zero. So whenever for whatever noise values there, they show that quantum computation is not possible, our noise values will be lower than that. So we are improving the upper bound on noise threshold. Especially for depolarizing, it will be strict improvement because there will be strict inequality between this and this quantity for depolarizing noise. Uh, okay, because there's something called non-degradability of the channels, which gives a strict inequality between these two quantities, which is not important. But what I'm trying to say is that our bound in on noise threshold will also be improved. Okay. Uh, and not only that, our bounds also directly extends to non-i.i.d. Noise at gates. So for example, think of a gate. As of now, the assumptions in all the papers, including what we have discussed so far, that noise at the output of the gate will be i.i.d. On each qubit, output qubit, the noise will work as i.i.d. But what if they're not? Because they're in the same gate, they can be correlated, can even be entangled. So in that case, our approach also extends directly. Instead of in tensor product G, which was capturing i.i.d. noise, you can put in G, which is a general G qubit noise. Okay. Just plug that in here instead of I in, sorry, again, I'm having this problem. I in tensor product G, it should be just ing, a general G qubit noise. Okay. So it extends to non-i.i.d. noise also at the gate. And not only that, these results extend to non-unitary computation. Suppose you want to use a quantum computer to do some non-unitary computation. To be honest, we don't know what is the practical application of that. But we could extend it, so we did. Mathematically, it was possible. So if there is application, there also our things extend. Okay. But as of now, we do not know actually what is a practical application of that. So that's why I just keep it in bracket. Okay. Any questions so far? If, I'll just move to the next thing then. If any questions, please ask. Hello? Am I
I
audible?
think there are no questions, so
Or
please
no question?
continue.
Okay, okay, okay. Thanks. Okay. So I'll, oh, sorry. I'll, so I conclude this part. So far we have only looked at quantum input, quantum output. So the thing that was in our mind was quantum Fourier transform. What is the lower bound on circuits like that, which are universally used in all classical, solving many classical problems. So the practical implications of our result so far is actually, it's always good to know the limit, how far you can reduce the redundancy. So we give that and we improve that limit, so which is good. Not only that, our thing is non-asymptotic. So this bounds that it derived does not have to wait for the fault tolerance era. It's actually applicable in the current NISQ era also. Okay, how good those bounds will be in practice, that yet to be seen, but they're applicable. They don't have to be asymptotic. Uh, okay, so that's one more thing. And also we think our bounds, it actually applicable to any noise and any gate size. And not only that, it applicable to correlated noise also. So it may help experimentalists in doing some kind of a first order planning. Like, so suppose there are few options for technologies and the experimentalists have to try experiments on all of them. And they're costly and time consuming experiments. At least with our bounds, wherever they can see the bound is really high for say certain technology gives you a certain gate size and certain kind of noise. Another technology gives you another gate size and another kind of noise. So one may compare across these technologies and kind of in the set of say 20 experiments that the experimentalist has to do, they may a priori kind of leave out 10 of them just by comparing these bounds and see, okay, the worst 10 worst bounds can be ignored. So and as this is a non-asymptotic bound, so this can be useful in this current experimental era also. So we hope that would be useful. Uh, okay, so this is the proof approach. I won't get here because I want to talk about something else, and we don't have. How much time do we have? Uh,
17 minutes.
huh?
17 minutes.
Oh, 17 minutes. Oh, good. Then I can talk about it. Great. Okay. So the proof approach is actually not hard. Actually, it's quite simple approach. The way we do, remember, this was our criteria. We wanted to have this. First, you observe that this is same as thanks to so the way the distance we use in our case is something called 1 minus fidelity, which I won't describe in detail. But the main idea is this is a distance, not in true sense, but is a useful distance. Okay. So what we can first show that this condition is equivalent to this condition. So if you have this output, you can pre-multiply with u dagger and post-multiply u and see whether it's close to rho n within epsilon. That's the first thing. For then what we do is, so what we say that, okay, then studying this circuit is same as studying the following circuit where I have this original circuit followed by a circuit which perfectly implements u dagger u and gives an output rho hat. So then comparing this less than epsilon is equivalent to seeing whether this rho n and rho hat n are within some epsilon. Okay. That's the first step. Then we say something more. We say, okay, we can give, as we are trying to find a lower bound on redundancy, we can allow more power to the circuit because we are trying to find a lower bound on redundancy. So what we'll do, we'll think of only the first layer has noise and the other layers don't have noise. Okay, and see what bound we get. Then we can call this whole later part as some kind of a joint circuit called script D. And the first part, this part before the noise as some circuit EC. Why EC and D? The names suggest this D is some kind of a decoder, EC is some kind of an encoder, and there is a channel. So what I'm trying to do here, I'm trying to send rho n, then encode it using EC, send it over a noisy channel, and then decode it to get back rho hat n. And this is where we establish the connection between communication and computation. Okay, this now becomes a communication problem, a quantum communication problem where you're going to transmit a quantum state over a noisy channel and recover it back. But with a small twist is that these encoders are not arbitrary encoders, they're constant encoder. That C captures that, they're constant. Why? Now they cannot create arbitrary states because these are G input, G output gates. So they, because of that, they can at the end of this gate this first layer, you can only produce certain kind of states, and that's why it's a constraint thing. And but still it's a communication problem and one can solve it, and the way to do it, the way to solve it is, again, as I said, this becomes a communication problem but a constraint encoder. But one can capture it using finite block length quantum computation but with a restricted encoder, not arbitrary encoding. And then what you can do, I am just skipping those details, is that you can connect this problem to something called multiple interdependent finite block length quantum communication systems. Like you can then reduce this constant encoder problem to something like a multiple interdependent finite block length quantum communication systems, and do some calculations using some kind of building on some known results for finite block length quantum communication. And you get finally that this n has to satisfy this equation, where this is a solution of a constant optimization problem. Okay, I won't get into the details, but after solving it, finally you get the bound that I wrote before. Okay, you have to solve it carefully, and then we'll get the bound. So that's kind of the logical steps towards the proof. And the main thing to notice here is that we try to boil it down and connect to a communication problem. It may not be directly a simple communication problem, but still a communication problem with a restricted encoder that then you can map to multiple independent, interdependent finite block length quantum communication systems, and then do some information, then borrow some results and build on that and get this bound. So that's the kind of the approach to the proof. Okay. So the intuition behind the proof is simple. Only the details I'm skipping. Okay. Now, as I mentioned, so this was all about quantum systems, like where the input is quantum, output is quantum. Okay. And previous bounds, including just what we talked about, they're all applied to those systems. But what about a specialized problem? Suppose I want to solve factorization only. I don't care about this Fourier transform engine being perfectly usable by all the algorithms. I just want to solve factorization problem. Okay. And I want to make my quantum Fourier transform tailored made for that. Okay. So what would be the redundancy bound in that case? And that's an important problem. One may say, okay, I will just make a quantum computer which will only break RSA codes. I don't care about anything else. I'm an adversary. So that's why I only need to solve fault-tolerant source factorization. Can I get better, or do the previous bounds apply here? The simple answer is the previous bounds, including the one we mentioned, do not apply in this setting where you are targeting a specific classical problem. Okay. And it can be shown by a simple example of something called a phase estimation circuit. Okay. This phase estimation circuit is something where you want to estimate phase of a, say, 2 power k cross 2 power k dimensional matrix. So suppose you have a unitary matrix U, which is 2 power k cross 2 power k, and it has an eigenvalue, eigenvector, which is psi, and it has a corresponding eigenvalue. And we all know unitary matrices have eigenvalues which are some, it's all on the unit circuit. Okay, so I just need to know the phase, and if I know the phase, I am done, because modulus will be 1. So there is a circuit to estimate the phase of this unitary matrix, and if in particular if the phase can be represented by a t bit, has a t bit representation, there is a circuit which recovers it perfectly. Okay, so this is the circuit. I won't get into the detail of the circuit, which recovers it perfectly. But this is under the assumption there is no noise. Now, suppose there is noise, and there is noise at a crucial juncture. So this part is quantum, and this part is something called the measurement. Measurement means after the quantum output, you want to recover theta by mapping the quantum outputs to classical through measurements. And suppose the noise creeps in between that. Okay. In that case, what will happen? What will be the bound? Now, all the known bounds, if I want to blindly apply them, whatever, including our bound, what they will say that, okay, suppose if I allow to change the kind of tweak this part using redundancy, all kind of techniques that you are allowed, and also tweak this part using redundancy and all kind of techniques, fault tolerance, encoding, everything. Even if you are allowed that, then what will happen? The existing bounds show that you cannot achieve accuracy, or you cannot do anything with non-trivial error if the probability of there is, suppose the depolarizing channel we discussed, if the P, remember the depolarizing P, if it's more than 0.33, nothing is possible. Same time, if something called erasure channel, where just the qubit gets erased, in that channel nothing is possible if erasure is more than 0.5. So that's the existing bound show. But there is a very simple scheme, very simple scheme. We uploaded a recent paper where you can do a very simple scheme which will actually get you any accuracy you want, like probability of error of recovering theta will be close to 0, even when noise is close to 1 in both depolarizing and erasure. It's a very simple scheme. So does it mean the previous bounds were wrong? No, it does not mean the previous bounds are wrong. The previous bounds, all the bounds, remember the criteria, they are on state distance. Okay, because they are looking at this universal or versatile quantum engine. But here we are looking at a particular problem, just recovering the theta. And here our main criteria should be probability of error of recovering theta. And when you look at that criteria, the previous bounds do not apply. And that's why they give this kind of misleading results. Nothing is possible beyond 0.5, but while we are able to do things close to 1. Very so this is a very different this I have just touched upon it, but it's actually independently very interesting. What we did, that we studied this kind of problems, we are interested in a specific classical output, and we could obtain lower bound on redundancy in those settings. Not only that, we also studied something very interesting, which was experimentally observed recently, is that when in quantum circuits you add redundancy, right, redundant qubits or redundant gates, they eat up the resources that are available, like including the cooling resources, the coolant, everything. And because of that, their exposure to the environment increases. And so by adding redundancy, sometimes actually are increasing noise. And this is called resource constant induced noise, because you have a certain resource for cooling and space and everything. By adding redundancy, you are eating up resource and you are increasing your noise. So the question is, if such a noise exists, and many systems, recent experimental systems have shown this kind of noise, then the question is, we cannot really assume the noise to be constant and get the fundamental bounds. We should study fundamental bounds in presence of this kind of noise. But unfortunately, the previous techniques were all kind of some sense asymptotic in nature, so they could not be applied to noise which is increasing as the redundancy increases. But our bounds are all non-asymptotic and depends on finite block length. So our bounds actually extend to there, and we studied that, and we got certain interesting results there as well. But I think I just wanted to mention that. Maybe some other time we'll discuss that in detail. So these, what I wanted to make, the point I wanted to make is, there is this quantum versatile engines if you want to study fault tolerance converse for them, and on the other hand, the specific classical problems that you're trying to approach, those two things should be studied differently, and the bound should be different, and that's kind of the takeaway of these two streams of studies. Okay. So said that, I would conclude. My time is almost over. So our main focus in this talk was on the quantum input, quantum output case. So there we studied tighter bounds on redundancy and noise threshold using finite block length communication. So we got gate size dependent bound. Remember, gate G showed up in our equations, IC and G. Our bounds are non-asymptotic, so they're applicable to intermediate scale noisy quantum systems, NISQ systems. And hopefully it will help experimentalists to kind of pruning out certain technologies and not experiment with everything. And not only that, our algorithms extends to correlated noise at a gate. Okay. And finally, we also talked about this classical output scenario where you're targeting a specific problem and resource constant induced noise. It just touched upon it, but yeah, it needs a thorough study. We are still continuing it. And said that, thank you very much again for the invitation, and also thanks for your patience. I'll be happy to take any questions if you have.
Thank you, Professor Chatterjee. We can take one or two questions. Can you please give an idea how this mapping is done from classical to quantum and quantum to classical?
Okay. So the way it's done is these classical bits can be directly mapped to certain quantum bits called orthogonal states. Okay. So it's kind of a direct map. It's like a 0 can be mapped to say an electron's upspin, and 1 can be mapped to downspin. After you get this quantum orthogonal states, then you can do certain quantum gate operations like Hadamard gate, C0 gates, many other gates, which will make then transform this orthogonal state into a proper quantum state, which may be entangled, the state that you desire. And after that, you do the quantum engine, the quantum computation on top of it. And at the end, you get a quantum state. From the quantum state, the way you come back to classical is through something called measurements. Measurements is like uh, it's like some kind of a converter from quantum to classical. There is a quantum system. You cannot really observe it quantum state. After you measure, you observe certain classical parameters associated to the state. And so if you design the measurements properly from the quantum state, you get these classical things back, classical parameters or the classical states back. And so that's how you do. So this is the pre-processing is the conversion to orthogonal state, then to quantum state, and post-processing, getting back to the classical state is the measurement.
Okay,
Does that?
thank you.
Okay.
So
Okay.
if there are no more questions, we can close this session. Thank you again, Professor Chatterjee.
Okay.
The
Thanks.
The slides and the link to the video will be available in our webpage. Thank you very much. Have a great evening.
Okay. Thank you. Okay. Shall I turn off the video? Okay.
Yes, sir. You can.